So I went to the University of Washington, and George Wallerstein and Paul Hodge were two astronomers from Berkeley who had, and originally from Caltech. Well, I had known George a bit at Caltech, where but then he went to Berkeley as a faculty member, and then they decided, he and Paul Hodge decided to, were asked to come to the University of Washington and sort of, there was an astronomer there who had been there for many years, but in terms of actually having a functioning graduate program in astronomy, they started it up. So this was then at the time when things were, the Kerr metric is being, there's the Penrose singularity theorem, 65, and the Kerr metric was being understood as a possibly general, stationary axisymmetric solution with a non-singular event horizon. So, so this sort of real understanding of black holes in more general terms was beginning around that time. So that, and then in '68, there was the GR5, which is in Tbilisi in Russia, which I went to, and that was interesting. So the talk I gave there was on showing you can construct a non-singular black hole, which the only reason it didn't violate Penrose's theorem was there was no Cauchy hypersurface. In other words, the space-time, there were parts of the space-time to the future of the collapse into the black hole that were not causally determined by an initial non-compact specific hypersurface before the formation, before the black hole. So, but then I made the mistake of eating some salad at this conference and got dysentery and had to stay stay over for about 10 days because I was quarantined in a hospital in Tbilisi. Then they finally released me, and I then had to go immediately. I mean, out of the country, back to the States. So I went from being in this hospital to flying sort of over 24 hours back to the United States. In the summer of '67, Kip Thorne organized a workshop at the Institut d'Astrophysique in Paris, which I went to. And that was noteworthy, mainly because I met my future wife there, who was from the U.S. She was from the U.S., but she was studying French. She was trying to teach French, and so she was at the Alliance Française in Paris trying to British French. She was and studying English in college, and was not, and taking a course or two in French, but but she was trying to teach French in a high school and junior high in Denver, Connecticut. But anyway, I was fortunate because in the fall of '68, Charlie Missner invited me to come to Maryland as, visiting professor sort of thing. And that was advantageous, both because I was closer to my future wife in Connecticut, and it was there I first got interested in cosmological perturbation theory. Actually, George Wallerstein, a friend of George Wallerstein's, Dick Mitchie, had tried to work out the fluctuations that lead to galaxies can grow in the early universe. And George had asked me, but he had died, recently, and so George asked me to look at his work and see if it was salvageable, basically. But I decided, there were some problems with it. But anyway, so I got interested. And that's when I first started to work on sort of gauge invariant cosmological perturbation theory, though I never published anything at that time. But this was like work out. Of course, this was before dark matter, so I was trying to do things in terms of a Friedman model, just ordinary, thermal gas, and but working out how things evolved during reheating. Now the sound waves before reheating went through the reheating process, and the damping, of the perturbations on smaller scales. So but then as I said, I never really published that, but I found, it's nice being, Charlie Minster was a good mentor. So I got married actually then in the fall, in December '68. And then we went back to Seattle in the spring of '68. And so, then I was interested got interested in things like, so I said, there was this non-singular black hole stuff, and I was doing work on relativistic, looking at various things related to relativistic stars still at that point. My first postdoc in Seattle was Jim Ipser, who had been a student of Kip Thorne's. Well, so one thing that's perhaps significant is there's still, not clear exactly how general the Kerr metric was at that point. And but so I did sort of, with Bob Wagner, I did sort of a calculation. We considered a uniformly rotating disk as a source for the gravitational field, and in the classical limit, this has a fairly simple solution. So it's a disk with a finite radius and finite mass, uniformly rotating, infinitesimally thin. Just a disk of dust, basically. And so what we considered was what happens as you try to construct, equilibrium stationary models of such a disk. In the limit, it becomes more and more relativistic. And I didn't know how to solve, any exact solution. So what we did was a post-Newtonian expansion, like 12th order. But by using Pade approximants to sort of speed up the convergence of the expansion and so on, it was fairly clear that the result, as this considered disk with smaller, given mass with smaller radii, that what happens is that the external metric becomes more and more like Kerr, the extreme Kerr metric. And so in the limit that the disk is sort of infinitely, well, in other words, the redshift from the disk, center of the disk to infinity becomes infinite. That in that limit, there's of course a region right around the disk which differs from the Kerr metric, but as you go out, there's this asymptotic region where essentially you're in the throat of the Kerr metric, extreme Kerr metric. sphere, not exactly spheres, but two surfaces of constant area going off over an infinite sort of range of proper distance but still, essentially r equal to m. So in terms of the circumferential radius. So we had a fairly convincing case that this was the Kerr-metric example of how you could get the Kerr-metric in the case of gravitational collapse. This was thinking sort of quasi-stationary collapse of a disk gradually shrinking down, and then the exterior metric becomes this extreme Kerr-metric. In the summer of '72, I went. It was the famous Les Houches Summer School, which really brought together most people working on black holes at the time, and was really when the idea of black holes as a sort of generic source of energy for possibly, people are studying accretion into black holes, and it's clearly, if you have a rapidly rotating black hole, you can get it up to 40% of the rest mass energy of accreting matter being released, the energy, which would be released in form of X-rays and so on. So it was, so that was, and by that time, Hawking had developed a lot of the theoretical ideas about generic, black holes. It was still hadn't been proven that the Kerr-metric was unique, but people strongly suspected it, and there was, it's good evidence that it probably was. So it's then when I got together with Steve Hawking and Brandon Carter to write the paper on black hole mechanics, and it sort of grew out of that summer school in a sense. So that was showing that so Steve Hawking had shown that the area of a classical black hole can only increase, can't decrease, can constant or increase. And Brandon and I had shown that the surface gravity of a black hole is uniform over the surface, so that so-called zeroth law, and the first law. So it was clear, these properties of classical black holes were clearly analogous to the laws of ordinary thermodynamics, but then, of course, we said that in the paper we wrote, it came out early '73, that this could only be an analogy because black holes were black and couldn't radiate. So it's a summer school, not a conference, right? So the attendees, so the students are graduate students basically, and to some extent postdocs, and it lasts, I forgot, 3 or 4 weeks, something like that, and there were lectures in the morning, and then usually you would be free in the afternoons to do other things, but either just informal discussions, or either informal discussions, or have or go on hikes. I climbed Mount Blanc when I was there for the Les Houches meeting. Well, I think that was on a weekend, but yeah. So it was a fairly relaxed atmosphere, and a lot of time for just general, having discussions, and as opposed, so it wasn't just all-day lectures by any means. It was more having, like, 2 or 3 lectures in the morning, and then you'd be able to have discussions in the afternoon, or go on hikes with people. So, so, well, in particular, this black hole mechanics paper was really, I mean, we had already done, basically, among us, the work, and so it was more a matter of putting things together, and so that was what we started, did a lot of it at this Les Houches Summer School, and in '72, and then it was letters back and forth, but sending but the ideas had already been pretty well basically settled, and it was just a matter of writing finishing the paper, basically. But then also in summer of '73, Stephen invited me to come and spend, some time in Cambridge, and so, we spent, like, I forget exactly, but two or 3 months in Cambridge at that time. And that was so we'd already, finished the black hole mechanics paper at that point, but it was still, it was an opportunity to get to know Stephen more thoroughly. Unfortunately, as Stephen went off into sort of this quantum gravity considerations and so on, and also as his got more and more difficult for him to communicate, we sort of didn't have that much contact in recent years. But we got to be good friends with his wife, Jane, and this is one of his sons, his oldest son, lives in Seattle, actually, working for Microsoft. He's now retired, but he has worked for a long time at Microsoft. So Jane comes to visit him and his family. Well, at least used to come once or twice a year, but with the COVID, it's been a longer hiatus. But so we made contact with her, and I've gone to some of the celebrations held in Stephen's honor, like his birthday celebrations and so on. But then Stephen, of course, within a year after that, showed that a couple of years out, showed that black holes do radiate, and that then founded the whole black hole thermodynamic industry, which is still going strong after over 45 years or more. So and then raised the question of all the questions about unitarity and so on. I mean, Stephen, of course, initial position was that for quite a while was that the fact that the Hawking radiation is entangled with Hawking partners inside the black hole meant that you would have a mixed state in the exterior of the black hole, not a, and that if you assume that the black hole evaporated completely, that it would be left with a mixed state, and which would apparently violate, quantum mechanics in the sense of the unitarity principle in quantum mechanics. And so that, of course, then huge controversy in industry of huge numbers of people working on it over the years. But I don't know. My own attitude was I was really more interested in black hole astrophysics rather than very sort of abstruse questions about it. Because I wasn't sure that anybody really knew how to do quantum gravity, for one thing. So I sort of bowed out of the whole, and didn't really follow that closely, all this business about quantum gravity and the question of black hole unitarity and so on. So actually then I did some more work in black hole astrophysics, but for a while I got interested in, based on this, looking at spiral instabilities of disks and how they might relate to spiral structure in galaxies. Nothing to do with relativity, but and some nice discussions with Howard Trumery at MIT about things of this sort. But then by the end of the 70s, in 1980, I came back to the cosmological perturbations, and I was stimulated by the fact that people were sort of claiming physical, physical significance for certain solutions of the cosmological perturbations, which were gauge dependent, and I didn't think that was right. So I went back to what I'd done earlier in 1968, 69, and sort of finished up what I'd started and wrote a paper on gauge invariant cosmological perturbations, which that's been the bane of many graduate students in relativity since then, I guess, having to study this paper. It was around that time that Alan Guth came up with Starobinski had done it earlier, but and Guth came up with the identity of inflation. And there was a famous conference organized by Steve Hawking in Cambridge in 1982, where this whole idea of inflation was being thrashed out and explored in more detail, and so then I got together with another major paper of mine with Steinhardt and Turner on how cosmological perturbations evolve through reheating and so on. And I have this famous zeta, I call them zeta gauge invariant amplitude for the cosmological perturbations, which was, even through big changes in the background question of state, like during reheating and so on, you could show was likely to remain constant. So it's a way of then connecting the in a rigorous way the initial cosmological perturbations to the perturbations which lead to large-scale structure in the present universe. And so then next, the 80s were mostly devoted to cosmological type things. So then in 83 or 84, there was at the Institute for Theoretical Physics in Santa Barbara, held a famous workshop on bringing together a lot of people working on inflation and large-scale structure of the universe and so on. And there I entered into collaboration with Dick Bond and Nick Kaiser, because, of course, the puzzle at that point was that there seemed to be some conflict between the value of the Hubble constant and or it's whether, well, the question was whether the universe is closed or not, and if you looked at the sort of simple models at that time, which did not, up to then, had not included dark matter, for instance, then it looked like the universe had to be open, but this led to conflicts with the age of the universe and so on. So, but the question of dark matter, of course, was the big theme of this workshop, and but even with dark matter, there still seemed to be some problems with getting things to work out properly. And so we wrote this paper on statistics of peaks and Gaussian random fields, having to do with biasing, and the fact that if you just look at high peaks, the clustering of high peaks is there's more clustering of the high peaks than there is of the overall field. So because you have sort of larger scale fluctuations, even if they're fairly small, it can make a big difference in the abundance of peaks above a certain high threshold. So, so that was an attempt to try to resolve this tension between what you in the data between what you it seems to be the amplitude of the fluctuations and the clustering of galaxies, and but of course that was finally resolved at the end of the 90s with discovery of the acceleration of the universe and cosmological constants, which then resolved that, at least went a long way to resolving that discrepancy. The people are still arguing about that a bit, but it's a much less tension than before. So between the value of the Hubble constant and the properties of large-scale structure. So anyway, and so I wrote some more papers with Dick Bond and other people about that sort of thing. And we're considering also alternative models of inflation, maybe more than one in Totan, and how they could affect things. But anyway,